Hi viewers, welcome to my channel. This is Antony Vijay. Today we are going to discuss about the various types of generative AI models. So in the previous video we have seen the introduction of generative AI as well as one of the type of generative AI models. So here we will see the second type. Let's see one by one. The first we will discuss about variational autoencoders, that is VAE. The goal of VAE is to compress the input data. The input data may be image or text that can be represented into the short form called latent vector. Then with the help of latent vector value we can recreate we can generate the realistic new data using compression representation. So in this VAE we have two different neural networks. One is compressor, that is called encoder. The second one is generator, that is called a decoder. The step one for VAE is input image. So here we have taken the input image of size 28 into 28 resolution and we are taking grayscale image, and the content for the image is digit 3. So 28 into 28 will be 784 pixel will be there. The values are between zeros and 1. Here 0 means it is black in color and 1 means it is white color. So 0 to 1 between that it will be a gray color. So it will be easy to process. That's why we have taken this small size image. Let's see the simple architecture of CNN or MLP. So initially the input layer contains 784 nodes. After that it is passed to the hidden layer which contains 128 nodes with the help of ReLU. ReLU is the activation function which takes only the positive values, and with the help of hidden layer the output layer contains only two values, that is mu and log sigma square. Mu means mean and log sigma square means it's a standard deviation. So each of them have two values. So in this latent dimension will be 2. So both of them will be producing two values, and the formula for mu is W mu into H plus B mu, and the same formula for log sigma square. Here W instead of mu we can use W sigma and H plus B sigma. Here H is the hidden layer output, that is after ReLU. ReLU is the activation unit, and W mu comma W sigma. W means it's a weight matrix, and the shape for weight matrix is 2 into 128. Here 2 is that is grayscale image, so 0 or 1. So this particular 128 value is passed as a map to 2. The same will be applicable for mu as well as log sigma square, and B mu and B sigma is a bias value. So this is applying for finding mu and log sigma square. The example calculation for the above unit will be, so for calculating the mu1 we have to use W1 transpose into H. H is a hidden layer unit output, then place B1. B1 is bias value. It's the same will be applied for mu2 also. Mu2 is instead of W1 we have to use W2 into transpose into H plus B2. So through this, while applying the value for mu we can get value like this is a example value. So here the value for mu is 0.6 and minus 1.3. After that here we have got the sample value for log sigma square is minus 0.8 and 0.2. Let's see. Now we have to convert this log sigma square into sigma. Let's have a formula for log sigma square. Let's see how to find log sigma square to sigma. Here we have to find exponential of 1 by 2 into log sigma square. Already the value for log sigma square is minus 0.8 we have seen in the last slide. While converting from this to sigma 1 we have to use, while applying 1 by 2 into 1 by 2 into 0.8, so it will be minus 0.4. It will be minus 0.4. So exponential of minus 0.4 will be approximately 0.67. The same formula again. Already in the previous slide we have seen the second value for log sigma square is 0.2. Again we are applying this. So here log sigma square is 0.2. Then we have to find sigma 2. Exponential of 1 by 2 into 0.2. It will be exponential of 0.1. The value will be 1.105. So mu value is already we got, that is 0.6 comma minus 1.3 example value, and the sigma square also right now we have got, it is 0.67 comma 1.105. So right now we have got the output layer values called mu and sigma. Now we have to find the latent vector in the terms of z. So z value is, if you want to find the z value, the formula is mu plus sigma into epsilon, and epsilon value is usually ranges from 0 or 1, and we can take assume we can take epsilon value will be 0.4 comma minus 0.9. Now find the value of z1 and z2. For z1 again we have applying mu value. Mu value is already, it is 0.6 plus sigma value is 0.67 into 0.4, that is a sigma value. So applying this we got 0.868. this is the z1 value that we are writing here. Then z2 again we are mu value is minus 0.13, it is writing here, and plus, and the sigma value is 1.105 into minus 0.09, that is here, that is epsilon value. While applying this we got minus 2.295. this is the latent vector value. So this is the latent vector. So we have applied 128 cross 28 size image. That image is converted into in the form of latent vector like this. This is what the latent format. So this particular image is compressed in the form of this. Then this particular z value is applied to the decoder format. So the decoder will convert, we take the value and reconstruct the image again. This is what called as variational autoencoder. Let's see the third model, that is autoregressive model. So autoregressive model is generally based on predictive model. This predictive model is based on past value. That past value, based on past value, it will find the current value. So here we are taking some of the examples, that is time series prediction. Here the weather, we can predict the weather, what is going to happen tomorrow based on today's situation, and what is the price of the stock based on today's situation. And language modeling, when I talk about language modeling, what will be the next word for this particular sentence. So this type of predictions. And image, so what will be the next pixel for this pixel. So we can find through pixel by pixel like this for image generation. And for audio, sample by sample. So these can be prediction can be done with the help of autoregressive model. And the main core idea for this, the future is always depends on the past. The mathematical term for autoregressive model is, here they are taking the order p for, that's a p number of iterations, we can do the summation process. And right now the current value is xt is the current value. If it is xt minus 1 is the past value. Based on the past value, current value can be generated. The formula is xt equal to c is constant, and this is the summation I equal to 1 to p, and pi I is a coefficient, xt minus 1 is a current value, plus epsilon t. Okay, this is the random noise we can add to the particular current situation. This is what called as autoregressive. So always xt minus 1 taking care of to find xt. This is what called as past can be used to find present. So let's see the example for this particular autoregressive model. So in this we have taken the first example is temperature example. Here we have taken previous 3 days of samples, and the formula for finding the current temperature is temperature T equal to 0.4 into temp T minus 1. T minus 1 means the yesterday's temperature, and T minus 2 means day before yesterday, and T minus 3 is 2 days before the temperature. While multiplying and adding these things and finally add with some noises, we got temperature like this, 30 degrees Celsius for T minus 1, and for T minus 2 is 31 degree, and T minus 3 is 29 degrees Celsius. Finally we are applying all those values to this Finally, we got 27.1 degrees Celsius for the current situation with some random noise, plus some random noise, that is epsilon t. So why it is called as autoregressive? So auto means self. It means past values fully depends on the present value. So here regressive means we can call it as a linear regression. There is a relationship between the current values as well as past values. This is called as regressive. Let's see the second example, that is NLP. NLP means we can have natural language processing. So that is we have to predict this next word for the particular sentence. So here it can do automatically. Let's have a look about the example called the cat sat on the. So this is the example. So after that, what will be this word will be there. So through this autoregressive model, we can apply the probability of match for the particular sentence. Accordingly, all the sentence ends with a dot. So likewise, we can go for probability. How already the probability value ranges from 0 to 1. Okay, likewise, we can find the major probability and apply on this. Through this, we can find the next word on it. And this particular sequential dependency is what makes autoregressive. This is the second example. And the third one is pixel by pixel. As I told already, pixel by pixel means it is for image generation. So usually we use pixel RNN, or you can use pixel CNN for generating an image based on the previous pixel. So right now I am in pixel 00. If I want to go to pixel 01, that is the next position. So this position depends on 00. And if I go to 02, so it's supposed to depends on 00 and 01. So the past one always useful for present one. This is what called as autoregression. And the fourth one is wavenet format. Wavenet is mainly for audio purpose. So here we have a sequence of waveforms like xt. Xt is the current form. So already we have some forms like xt minus 1, 2 and xt till n. N number of samples are there. Based on that, we can apply this in the function and we can find the xt. This is what called as wavenet. So again, with the help of this, we can find the stock price also. So currently we have a price called 0.8 into price t minus 1. T minus 1 is the past value. We can find the current price with the help of price t. So right now we can know the price of yesterday's stock, that is 100. So 0.8 into 100, it is around 80 plus some noise. So through that we can find the stock price of certain stock. So this is the examples of autoregressive model. Next model will be diffusion model. In this diffusion model is usually called the generative model. So this particular model can learn to generate new data like images, and by learning how to reverse gradual noising process. So in this we can add some noise. One part will be adding some noise, that is called the forward process, and in the backward process we can denoising the image. So this is what the general process is happening in the diffusion. Let's see the clarity about this. So imagine taking a clear photo called gradually adding some noise. So gradually means step by step we are adding a noise to your image until the completely the image full of white noise. A diffusion model learns to reverse this process. Especially this particular model can do the reverse process to clean the photo one step at a time. So step by step, t minus 1, t minus, like each step it can do the denoising process. So in this particular model there are two processes. One is noising process, the other one is denoising process. To generate new realistic samples like photos from cat, people or whatever maybe, so starting with the pure noise, after that we denoising it through the learned network, because for denoising also we need some knowledge from the neural network. So these to be happened. Let's see how it is working detail. Let's see. First one is step 1, that is forward process. We are adding noises repeatedly in the form of step by step. Initially we are taking a clean image, that is x0. After that we are adding some Gaussian noise in the form of t steps. So x0 to x1 the image has some noise, and x2 added some more noise, and finally in the xt it's full of noise. It is pure noise. Your image is full of noise is happened. That is called step 1. Okay, let's have a look about the formula for this particular noise process. So q of xt given xt minus 1. So noise of xt 1 minus beta t xt minus 1 beta t. So here x0 I already told you that is the original image. So after each and every step small noises are added, and beta t means we can find the noise variance, how the variance is happened between t minus 1 to t minus 1 to t minus 2. So there is a difference. That gradual variance we can find with the help of beta t. So this is what this particular process is happening till xt t steps. Now we can do the denoising process. So that reverse process. So initially we started with this x0. Now we started with the xt to t minus 1 till x0. This is what happening. This is called the denoising. So we can train the particular process about the noise. In order to find denoising the particular image, we supposed to know where the noise and how the noise will be. That particular training process supposed to be taken from the neural network. Here epsilon data of xt comma t, it will keep on tries to predict the noise from each step. So this particular network is generally for minimizing the error. Let's see the formula for denoising process. So Ex0 means that is the input image, t means t steps, and epsilon means some random noise of, we have applying the gradient formula, that is epsilon minus epsilon data xt comma xt the whole square. So while applying this for finding the random noise, through that we can iteratively we can denoise the process to get the realistic image once again. Now the third step for this is image generation. So this noise process gets started and the reverse process are already over. So finally the result is x0. So initially we start with x0. So we reached to xt with full of noise. After that we are from xt we are reversing the process to x0. Now this is denoising. So this is pure image. This is what called as diffusion models. Next model is transformers. So the transformers is mainly for doing some natural language processing. So it's mainly for natural language processing. Previous methods like RNN, that is a recurrent neural network, or long short term memory, were very slow and they very struggle to find the next word or prediction and all. It's very difficult. So that purpose we are introducing transformers in it. So there are some two different drawbacks from RNN and LSTM. The first one is long-term dependencies. Actually, this particular RNN and LSTM are very difficult to remember all the words in a sentence very long back. It is very difficult. For example, a sentence have 30 words. If you are remember all the 30 words, it's very difficult for RNN and LSTM. So that's supposed to be remember, but transformer do all those things. And the second one is parallel computations. So we have to process word by word is very slow. So we have to process all the 30 words in a sentence at a time. So that parallel computation is very important. So these two drawbacks from RNN and LSTM, that's why we are moving to transformers. So transformers fix means solving the issues, solving the above two issues by using self-attention. So self-attention means it can look out all the 30 words. Example, I'm saying 30 words in a sentence at a time and focus what is important and what is going to come next. That prediction can be done very easily with the help of transformers. Let's see the architecture overview. So initially we are applying an input sentence, then we go for embedding process. After that we go for positional encoding. It's like tokenization. We are assigning an index value for each word, that is called position encoding. And multi-head self-attention means at a time all the words supposed to be taken care of. It should not be word by word. Okay, then we are applying to feed forward network plus normalization, some unnecessary words to be normalized. Finally we get some proper predicted word. Okay, this is what called as transformers. So in the first layer we have seen embedding plus position encoding. So each and every words are converted into vectors. I told you in the previous model all the images are converted into the compressed form called the latent vector. Likewise here also words are converted, because this particular transformers is mainly taking care of natural language processing. Natural language processing, obviously we only deals with the English words, like words only. So these words are turned into or converted into vectors using a lookup table. This particular table has all the words for a sentence. After that we have to assign for a positional encoding. Positional encoding means on that table we have to assign the index. For example, this word, the index for this word is 0, 1, 2. Likewise we have to assign for each word position. So for example, I have taken the cat sat on the mat. The cat sat on the mat. So each word becomes a vector plus a number that encodes its position in the sentence. This is the first work for a first layer. Next we will see about the second layer, that is called self-attention. That is key innovation. So here the model may decide which words to focus on based on the current word. Based on the current word, it will check the previous words in the sentence. So accordingly it will check the which word supposed to become next. For example, for every word we have to calculate QKV, that is query, key and value. The formula for is attention of QKV equal to softmax of QKT square root divided by square root of DK into V. This is the formula. While applying this formula, we can get some weightage for each word. So automatically highest weightage value or word will come next to the certain particular sentence. Next, see the third layer. In the third layer we have seen multi-head attention. So in the parallelly we have looking at all the words at a time. So all the results can be combined at a time. So through that we can find the relationship of all the words with each other. Based on that we can easily find which one come next. Then we go for feed forward neural network, which contains 2 layers of neural network and each one has some tokens for it. Then we have to remove some of the unnecessary words to get a deeper result, that is called a layer normalization. So through that we can get some proper results. For example, the model is processing the word sat. It can be used self-attention to focus on what is sat. Before that, the cat word is there. Cat word is representing the one of the third person singular, that is who. And mat means it's an object, so where we are sitting, so that is where. So likewise we are keep on taking care of NLP on this. Accordingly we can go for predicting the next word. So next we are seeing about LLM, that is large language model. So this only taking care of massive text database, and it can predict the next word and generate the next coherent text and how to translate, summarize and answer questions like ChatGPT. It can be act as a ChatGPT. ChatGPT also using this LLM technique only, because for a single ChatGPT they have a lot of data to be required for training all those things. then only we can get the proper approximate around 98% of result is correct only. Sometimes around 2% some mistakes might be there. Okay, so for this we need some characteristics in order to working like this. We need some characteristics like first one is model size. So model size will be very high. It is billions of parameters because we are dealing, this is large language model. It is not a normal one, so it's dealing with only massive one. Then billions of parameters are there. It's like GPT-3, it is around 175 billions of data, and GPT-4, it's the next version of GPT, it is even larger. And the next one is training data. So how it is answering answers for questions. So that is only because from trained on books, websites, code, medical text. So all these things are running behind. Then only it can able to answer the questions from us. Okay, this next one is output. So text can be generated for our questions, and question and answers, whatever questions you are asking, we will get some answers. And if you are summarization, that's also done. And for coding also we are getting, and for reasoning all the reasonable answers are we are getting. Okay, and when we talk about architecture based on transformers, it is dealing with the decoder, encoder, or both. And the input format is fully taking care of tokens, that is tokenization, that is NLP model. And learning objective is next token prediction or masked token prediction. So this particular LLM is mainly for developing like ChatGPT. So it is full of memory, has trained books and websites, code, medical text and all. Examples of LLM, there are various LLMs are there, like ChatGPT, like various BERT is there, T5, LLM, and Claude is there, Gemini is there, GPT-4 is there, it's a new version. So each one is having some new types. One is decoder, and BERT is the encoder one, and T5 is the encoder decoder model, both. And LLM is decoder only, and Claude is Gemini, and GPT-4 is decoder only. And the purpose of GPT is only text generation. We can do the image also, but for image generation it takes very longer time to get answer, so it is very difficult. So if you want to do some image generations and all, we go for Midjourney and all. Midjourney, this is the best one, or we can go for DALL. These are the two different models are good for image generations. And BERT is mainly for text and question and answers, and T5 is for translation and summarization, and LLM is for research focused open LLM, and Claude, Gemini, all the things are doing for multi-purpose assistance. Multi-purpose, but generally speaking these things are good in text generation other than image and video and all. Okay, this is about a large language model. And let's see the working of LLM. So for example, I have an input of what is the capital of France. So first of all, it will do the position of each words with the help of tokenization. So it is splitting the sentence into words like this. So what is the capital of France, question mark. So likewise it will convert the words into vectors like this and do the position encoding process. And finally they can do the finding process, like they can find the relationship between each words, and finally it is producing the answer called the Paris. This is what the general process of large language models. And let's see the difference about the transformer versus LLM. So when I talk about, this is a transformer column and this is LLM column. So in this purpose, it is mainly for transformer is like a architectural design, but LLM is for large model. It's a very large model, but here the size is very small to medium, but it is very large. And transformer can be used in NLP and vision, but here it can do for coders, generators and chatbots, AI assistants. For all bigger things can be easily done by LLM. And a transformer can be done only with the help of attention based, but here we can do all the things like language patterns, semantics, grammar, knowledge, everything can be easily done by LLM. This is what the difference between transformer versus LLM. Let's see how the generative model works. So here Initially we are having a training data in the form of image, text, audio, video, whatever maybe. Then we are applying to the generative model. It's like GAN, VAE, diffusion, LLM, like various things we have seen now. So after that we are converting into the latent form, already in the compressed form. We have seen the formula for like mu and epsilon and all. So with the help of that we have find the z is a latent vector. So from that we can regenerate the new image. This is the new image. So this image and this image are supposed to be different. That's why it is called generative model. And in this we can see a lot of human faces and all. And so as I told already, latent space supposed to have in the form of single dimensional, like in this form. So we have got the new image, new smiley image. This is what called as thing. Okay, please like and subscribe to my channel and press the bell icon for regular updates. Thank you very much for watching.